The ideal gas laws allow us to characterize a variety of gases at various conditions. And mostly what we're looking at with these equations are going to be pressure, P, volume, V, number of moles, N, and temperature, T. Now, I'm just going to go ahead and get ahead of something really quick and let you know that whenever we're measuring temperature with ideal gas law equations, we need to make sure that we do our calculations in absolute temperature, which means we take that degrees Celsius and then we add 273.15, and that's going to get us our value in Kelvin, which is our absolute temperature. So let's start here on the left looking at a particular experiment involving measuring the pressure, measuring the volume, but we're going to keep the temperature constant and we're going to keep the number of moles constant. And we're going to see what the effect is of modifying the volume on the pressure. So what we're going to do here is we're looking at a 100 milliliter container with a pressure of 760 torr. And the first thing we're going to do is half the volume. So our volume is going to go down. And what happens to the pressure? Well, the pressure is actually going to double. So our pressure goes up. And so then we do the exact opposite. We double the volume, so the volume goes up. And you might guess what's going to happen to the pressure. The pressure gets cut in half. So the pressure goes down. Now this as a whole is what we would call Boyles Law. And here's what it looks like mathematically. If we take the initial pressure, we can multiply it by the initial volume. We can set that equal to the final pressure times the final volume. And mathematically, this is an inverse relationship. And it will model this exact phenomenon that we observed in the experiments. Now the second experiment we're going to do, we're actually going to hold the pressure constant, but we're going to see how the temperature can affect the volume. And so what we're going to do is we are going to half the temperature. And what happens, we actually see that the volume gets halved as well. And then if we double the temperature, the volume doubles as well. And this gives us what we would call a direct relationship. And this one is called Boyles Law. And mathematically, a direct relationship can be modeled like this. The volume initial divided by the initial temperature is equal to the final volume times the final temperature. And just as a recap, this is indeed a direct relationship. So our last experiment is going to be called Avogadro's Law. And Avogadro's Law is much like blowing air particles into a balloon. If you add moles, you should see that the volume increases. If you remove moles, you should see that the volume decreases. So let's take a look at it in the context of this experiment. When we removed 5 moles, which would be half the amount that you have here, your volume cut in half. So as N goes down, volume goes down. But if we added 10 moles, that would be doubling the amount that we had in this initial container. Our volume doubles. So N goes up, volume goes up. And so this is going to look a lot like Boyles Law mathematically, except now we're dealing with Avogadro's Law, and instead of temperature, we're dealing with number of moles. But it's still a direct relationship, so it still looks like this. But now we're just dealing with number of moles and not temperature. So very similar equations there. Now we see that volume exists in each of these relationships, and so there is a way of making sure pressure and temperature have a relationship, pressure and number of moles. And instead of taking you through each and every one of those, I want to give you the more valuable equation that combines all of these together. And that would be the ideal gas law equation that looks like this. PV is equal to nRT. And this is just going to combine everything, where anything on the same side is an inverse relationship. Anything on opposite sides is going to be a direct relationship. The only thing that I haven't talked about of these terms here is this R value, and that's the universal gas constant, which you're going to see in two different ways on formula sheets and conversion sheets. First of all, there is the 0.08206 liter atmosphere over mole Kelvin, and then there is 62.36 liter torr over mole Kelvin. And so the question is, how do you know how to use this universal gas constant? Well, what's the purpose of the constant at all? Well, it's always going to be to make sure that your units on the left side of the equation are properly communicating with your units on the right side of the equation. And in terms of gas measurements, in volume, we're typically dealing with liters. For number of moles, we're always just dealing with number of moles. And for temperature, we always have to be in our absolute temperature Kelvin. Now, pressure can be different, but it's typically going to be either atmospheres or torr. And if you don't have one of those units, it's smart to convert to either atmosphere or torr. And let me show you why that is important. Well, if this pressure here is measured in torr, all of a sudden I have torr times liters on the left, and I have mole and Kelvin on the right. So I need to select the R value that corresponds to my pressure unit here. Because look what happens when I use this 62.36. If I use 62.36 liter torr over mole Kelvin, when I multiply all this through, my mole will cancel out with my mole, my Kelvin will cancel out with my Kelvin, and I end up with liter torr on both sides. So to really summarize and simplify what I just said, for the ideal gas law equation, you always use the R value that matches the pressure units in your equation. So let's see if we can handle that concept with a sort of silly application question. And this is that a patient has a vital lung capacity of about 4.8 liters with an internal pressure of 1.44 atmospheres and a temperature of 37.0 degrees Celsius. Now, a vital lung capacity is just going to be the maximum amount that that patient can exhale. And so the question is, how many moles of ideal gas are in a sample of the gas collected from that single exhale? And so when I'm looking at this question, what I see is a bunch of my terms. I see pressure, I see volume, and I see temperature, and I'm asked for the number of moles. So this is a perfect question to use your PV is equal to nRT, because my pressure is 1.44 atmospheres. My volume is 4.8 liters. My temperature is equal to 37 degrees Celsius, but remember, I need to turn that into absolute temperature. So I'm going to add 273.15. That's going to be 310.15 Kelvin. And then I do know what my R value is because I know what my pressure units are. And so I need to select the R value that matches my pressure units. So that's going to be 0.08206 liter atmosphere per mole Kelvin. Now I can rearrange to solve for my N term, which is the number of moles. So this is going to look like this, where N is equal to PV over RT. Now I'm going to do my best to write out all my units here to really show how everything cancels out. So I have my 1.44 atmosphere times my 4.8 liters divided by, and this is where the units get pretty crazy, so my RT, so 0.08206 liter atmosphere, mole, Kelvin times 310.15 Kelvin. So let's cancel out these units. So I've got atmospheres and liters up top, which are going to cancel with liter atmospheres down here. And then Kelvin times Kelvin. And so I've got an inverse mole on the bottom, which translates just to a regular mole on the left side of the equation. And so my units do cancel out properly. It is pretty hectic, but it does cancel out to give me moles in the end. And so my final answer is going to be equal to 0.27 mole. Now, before we end this video, I want to just do a quick recap on what we talked about. We talked about 3 individual gas laws. We talked about Boyles Law, Charles' Law, and Avogadro's Law. And we talked about how we can conceptualize each of them and an equation that goes with whether they are an inverse relationship or a direct relationship. Now, those individual gas laws are important. We do want you to know the name of the law and associate it with the equations and the concepts behind it. However, you're going to find yourself using that PV equals nRT formula quite a bit in chemistry. And so you want to get very comfortable knowing how those units cancel out and knowing how your R value works to get you to the final answer.